Did you ever wonder why the Earth looks the way it does? Why the morning sky is sometimes painted red? Or why a rock wall stands here and a desert there? Why does a huge boulder seem to defy gravity? And how did a peaceful river cut its way through solid rock? As scientists explore the Earth, they ask similar questions. Questions they hope will lead to a basic understanding of the Earth and how it came to be the way it is today. They often begin by examining rocks.
What is the Earth made of? Where did this particular rock come from? And how did it get here? These and related questions have taken geologists to some pretty exciting places, to great depths, and to some frightening heights. In the next few minutes, we're going to meet some very interesting scientists, people driven by their own curiosity to the very frontiers of Earth science.
Dr. Robert Christensen of the U.S. Geological Survey has spent more than 30 years unraveling the geological stories woven through the rocks. To him, rocks are clues to the Earth's past. By studying rocks, Dr. Christensen believes he will come to understand how our planet evolved into its present form.
Okay, let's look at the top here. All right, this is a good spot to see several different kinds of rocks and the relationships between them.
All right. Well, once you pick up a rock, how do you figure out what's inside?
Oh, well, that's an important matter. Usually what I would do is get out my hammer and pick up the rock and give it a crack and look at it. Because when you look at the unbroken surface, you notice how the weather has altered it, changed it, so that you really have a hard time identifying what it is. But if we turn over where I just broke the surface, you can see that the rock is actually made up of many different small pieces. Each of those pieces, the material of each of those pieces is a mineral. So the rock is made up of minerals. Now, a lot of people don't realize that there's a difference between rocks and minerals. They tend to think of these as being the same thing, but they're really not. The minerals are the individual materials of which the rock is made, whereas the rock is the whole thing. It's sort of as if the minerals are the trees and the rock is the forest.
Oh.
So what we want to do in order to identify the rock, know what kind of rock it is, first we have to identify the minerals. So we look at it, we see what the color of each particle is, each grain. We see the shapes they have and the way they fit together. Also notice where I've broken it, we get reflections. As I move the rock around, we get different reflections off the broken surfaces of different mineral grains.
There's some shiny parts.
That's right. And the way each type of mineral breaks is also different, and the intersections between the surfaces of breakage. So we put all those things together in order to identify the minerals from the rock. What we really want to know is, what's the origin of this rock? How did it get here? What's its significance in finding it in this place? How did the landscape form from these rocks and from the soils that formed from these rocks? So those are the bigger questions we really want to get at. So here's the map on which we've been keeping a record of the various kinds of rocks that we've seen.
A geological map enables Dr. Christensen to put all his information together in one place. His maps then show patterns, and from these patterns, he formulates his next set of questions.
The ability of scientists to answer difficult questions has always been limited by the tools they had. With the hammer, the magnifying glass, even the map, geologists could only examine the surface of the Earth. Curiosity about what lay beneath the surface drew them to places such as the Grand Canyon.
The Colorado River has carved out, perhaps, our most penetrating view of the Earth. Here, layer upon layer of our planet's history has been exposed by the forces of nature. Wind and water have slowly but relentlessly sculpted and exposed a trench 16 kilometers wide and almost 2 kilometers deep. Over the millennia, the river has eroded its way backward through time, down through millions of years of accumulated stone, slowly exposing Earth's past. The exposed rock is like a geological library. You can find a volume in this library on flooding, when an ocean covered the land, and another on uplifting, when the land rose above the sea. You can read about rocks being formed and rocks being destroyed. It's all there, written in the walls of the Grand Canyon. But while 2 kilometers of exposed history seems like a lot, it represents a mere scratch, a moment in time. Until quite recently, scientists had trouble looking more deeply into the Earth's past. In the late 1800s, scientists studied some unusual iron fragments found around a great hole in the Arizona desert. It turned out that these fragments were very old, about 4.5 billion years old, and had survived the ultimate crash landing.
Imagine 49,000 years ago, a huge meteorite traveling through space at enormous speeds struck the Earth here near Winslow, Arizona. The meteorite blew a hole in the desert more than 200 meters deep and almost 2 kilometers wide.
Scientists think that meteors were formed at or around the same time and in much the same way as the Earth itself. For billions of years, these meteorites have been crashing into the Earth. Meteorite fragments, scattered across the surface, now give us clues about the composition of our planet itself. Dr. David Roddy of the U.S. Geological Survey has spent much of his lifetime following those clues.
How the Earth began, what's happening to it, and what it's made of.
Well, Mike, meteorites, asteroids, and comets are where the Earth comes from. It's what makes up the Earth. And early in solar system time, these bodies were all colliding with each other. And if they were at speeds that were appropriate to stick together, they stuck together, made a planet. That's what our planet is made of. Iron from meteorites, silicates from the asteroids, and water from the comets. As a matter of fact, what do you think that might be, Mike?
I'm not sure. It's pretty heavy.
See if it's magnetic.
Yeah, I can feel the pull. Is it?
That's part of the Canyon Diablo meteorite that formed Meteor Crater 50,000 years ago. Solid iron.
Scientists have learned that the raw materials from which the Earth is made came from space, from meteorites, asteroids, and comets. But today, the Earth seems quiet, even stable.
We're used to seeing landscapes that don't seem to change at all in our lifetimes. That's a mountain, there's a valley, and this appears to be a solid rock. So it's easy to get the impression that the Earth and all its parts are static, unchanging. But it would be a mistake to judge the Earth from the perspective of a human lifetime. The Earth is very likely a 4.5 billion year old planet. Viewed on that time scale, the Earth is anything but static.
In fact, the Earth is continually changing. Through the millennia, wind and water have slowly chiseled out nature's artworks, particle by particle. The erosion process is eternally molding and remolding the face of the Earth. But it's not just the surface of our planet that's changing. Once geologists developed tools capable of looking deep inside the Earth, they found evidence of heat energy at work. One of the first scientific instruments geologists used to probe beneath the Earth's surface was the seismograph. Seismographs are the primary tool used to detect and monitor deep Earth movements. The shock waves caused by as many as 1 million earthquakes per year can be monitored and printed out on slowly rotating drums.
I saw the machines in the other room. How do they know when an earthquake has occurred? What
you saw up in the other room, those are recorders. There are sensors or seismometers, either one you want to call. They are throughout the whole United States and many parts of the world, and the sensor or the seismometer could be buried at different depths in the ground. We try to get these sensors or seismometers on bedrock. And so when the shock waves travel through the earth, these sensors will sense that, and they send that signal to our office here, and they record it on the recorders.
What do those shock waves look like?
This is what a wave looked like. This is a recorded earthquake here, and you can see the lines here. And to the kids is a wiggly line, but here it says P. See, this P says P arrival. Well, that means that everything is going along very quietly. Then all of a sudden, the waves is reaching the recording station, and you record the earthquake. That's the P wave, the primary wave, the longitudinal wave, the fastest traveling wave in an earthquake.
Much of our knowledge about the interior of the Earth comes from the study of shock waves sent out by earthquakes. Seismic waves take several forms. Secondary, or S waves, can't pass through liquid. Their paths tell us that the outer part of the Earth's core is fluid. The primary, or P waves, can travel right through the Earth. All seismic waves change direction as they slow down or speed up, according to the varying density and composition of the deep interior. Guided by these waves, geophysicists have learned our planet contains a series of layers. The surface upon which we walk is a thin skin composed of Earth's least dense rock. This uppermost layer, called the crust, is part of the lithosphere, which floats upon another relatively thin, somewhat denser, and partially molten layer of the upper mantle, called the asthenosphere. Much of the asthenosphere is so close to melting that it deforms plastically, like warm taffy. The Earth's density, temperature, and pressure continue to increase with depth. Here in the core, which is mostly iron and nickel, we find a molten outer layer and a solid center. Seismic waves have helped scientists map the Earth's interior, but no one has ever actually traveled to the center of the Earth. So how do they know what the Earth's interior is made of?
Well, some of the answers are here in Hawaii, on the flanks of one of the most active volcanoes in the world. To geologists, volcanoes, such as Kilauea, offer a window into the Earth's center. They study what comes out of the volcano and learn a lot about the mantle.
Clouds of steam signal the contact of cold water and hot lava, ocean meeting mantle. A volcano such as Kilauea is one site where some of the Earth's immense internal heat energy can be seen at work. Like a great planetary kitchen, the mantle and the volcano work together, cooking up new rocks and minerals. It all begins on the awesome edge of the active volcano.
So what kind of things can you learn about the mantle from volcanoes and their eruptions?
Well, volcanoes, as spectacular as they are, probably among the most awesome sights there are on the surface of the Earth, are really just the topmost portions of systems that go deep into the Earth. Mm-hmm. And their roots are down in the mantle. So we get this partial melting of the mantle, and the molten material, which we call magma, is less dense. It's not as heavy as the rocks around it. So it tends to rise, just like oil will rise through water and spread out on the top of it. So the magma tends to rise from the mantle up into the crust and erupts in the form of lava. So the rocks of the crust then include both these igneous rocks, as we call them, the rocks that originally came from magmas, that some of which originally came to rest within the crust, others of which built out upon the surface of the crust. Both types of igneous rock help make up the crust.
Much of the Earth's crust was created by volcanic activity. Lava pouring out on the surface cooled, layer upon layer, and eventually built islands, mountains, and plains.
So the crust is made out of igneous rocks.
Probably the original crust of the Earth was formed of igneous rocks, but there are other kinds of rocks in the crust as well. Many things happen to rocks once they come to rest within the crust, or especially on the surface. The weather has an effect, erosion occurs and moves the fragments that are formed by breakdown of the rocks. It moves them out into rivers and lakes and oceans, and these materials, these fragments, become deposited as sediments. And as sediments pile up one on another, they eventually become hard. The ones down below become hard and form what we call sedimentary rocks.
Oh, so like sandstone, because you can see the little
That's
layers.
right. Sandstone is a good example of a sedimentary rock, which is another kind of rock in the Earth's crust.
So those two rocks are what the crust is made of then?
There's actually a third kind as well. So all rocks are either igneous, metamorphic, or igneous, sedimentary, or metamorphic. Metamorphic rocks are rocks that were originally either sediments or igneous rocks that have been changed by being pushed back down into the Earth, where under conditions of high temperature and pressure, they become crystallized again and become what we call metamorphic rocks, or changed rocks. So you can see, in a certain sense, there's a cycle to the way rocks are formed, from igneous to sedimentary to metamorphic, and maybe back to igneous if they become melted again.
Just beneath our feet, on the flanks of Kilauea, a river of lava flows toward the sea. And in Wyoming's Yellowstone National Park, steam vents, geysers, bubbling mud pots, and boiling pools of water are all hints of a dynamic heat engine at work a few thousand meters beneath the surface of the Earth. This engine is driven by a combination of heat left over from the Earth's formation and radioactive decay on a grand scale.
Our planet's interior acts a lot like a giant nuclear reactor. Unstable isotopes of some elements, such as uranium, potassium, and thorium, slowly but continuously disintegrate, releasing heat. And that heat can cause groundwater to boil and even erupt into the air.
The heating process under the Earth's surface is uneven. In some places, material heats up and rises. In other places, it cools and sinks. Scientists think these differences may cause massive currents, called convection currents, in the mantle. These scientists theorize that convection currents have forced the Earth's crust to move and break apart into giant slabs or plates. The famed San Andreas Fault in California is a site of two plates sliding past each other, slowly deforming under the forces of friction. At other sites, plates slowly collide, folding and crumpling the Earth's surface. They can slip under or ride over each other, slowly pushing up mountains.
It stands to reason that if there are places where these crustal plates are smashing together, there must also be places where these plates are spreading apart. In the late 1950s, oceanographers found that a ridge system on the ocean floor encircled the entire globe. The spreading of the Earth's crust occurs at these ridges.
Studying the creation of new ocean floor has become a fascinating full-time occupation for geologist Dr. Rachel Heyman of the University of California at Santa Barbara.
Mid-ocean ridge. The mid-ocean ridge is a volcanic mountain chain, more or less, that extends all through the oceans of the Earth, all around the globe, and it would look a little bit like a seam on a baseball, and it's been described often that way. Now, it's the edge of two plates that are pulling apart from one another, okay? So it's where those two plates are joined, and they are pulled apart. Lava from deeper in the Earth, from the upper mantle, rises and erupts at the mid-ocean ridge, and also freezes underneath the seafloor to form the plates that are the ocean floor. Now this keeps happening continuously. The plates are pulled apart along this rip, which is the mid-ocean ridge. Lava will then keep coming up, freezing, pulls apart again, lava comes up again. So it's an ongoing process by which the ocean floor is created.
Since most of the action occurs deep underwater, inquiring scientists have harnessed new technologies to explore the unknown frontiers of mid-ocean ridges. Fully equipped high-tech submarines like the Alvin can be piloted as far as 5 kilometers under the ocean's surface to view, record, monitor, sample, and report.
A2 Alvin, hatch is shut, oxygen's on, CO2 scrubber is on, leak stumps and grounds are normal, ID lights on, vent valves open, tracking's on 8.1.
X5446Y.
It was from the Alvin that Dr. Heyman observed the aftermath of an underwater volcanic eruption.
Doug just told me something so exciting that I started stuttering. He sees a tube worm sticking up out of this lava that's still alive, which means that whatever caused all this carnage down here happened not very long ago at all.
Standing on the very edge of the unknown, at the frontiers of knowledge, Earth scientists feel a sense of excitement. As they stretch to understand the Earth, we all benefit. Already, they have taught us a great deal about the Earth we live on.
So, what have we learned? We've learned where many of the materials which make up the Earth came from. Asteroids, meteorites, comets. We've named many of those materials. Iron, nickel, the silicates, water and atmospheric gases. And we've examined, briefly, the process of change on Earth. How the lightest materials float and the heavy stuff sinks towards the Earth's core. How rocks evolve and cycle. And we've shown how the dynamic flow of energy shapes Earth's features. Many of the tools which we started with are still with us, yet there are many more. Some very sophisticated. And as the tools keep developing and our understanding improves, the questions just keep getting better.